Welcome to today's webinar, Deep Dive on Amazon Redshift. Our presenter today is Tony Gibbs. Tony is a member of the Big Data Specialist team at AWS, where he focuses on data warehousing solutions for Amazon Redshift. Prior to joining the Big Data Specialist team, Tony worked as a software development engineer at Amazon Destinations. Tony holds a bachelor's degree in computer science and economics from the University of British Columbia. Today with us, we also have Ho Hong and Peter Dalton, who will be our webinar moderators today, answering your questions through the Q&A panel. Tony, welcome. The floor is now yours.
Hi, I'm Tony Gibbs. I'm, as introduced there, I'm a solution architect on data warehousing for Amazon Redshift. And today I'm going to be talking to you guys a little bit about query lifecycle and parallelism and kind of the storage subsystem in Redshift. So we'll just get started here, just kind of looking over the agenda. We're going to start out just kind of with a kind of an overview of the history and development of Redshift, just to kind of give you guys a bit of, just an overview really. Then we're going to jump into the cluster architecture so you guys kind of get a bit of an understanding of how Redshift works. And then we're going to jump into kind of concepts, terminology, so that we can kind of build up towards the rest of the webinar. Then we're going to jump into the kind of the parallelism, and that's kind of where we get into the query lifecycle and all that good stuff. Then at the end, I put in for you guys a bit of the new and upcoming features that are coming to Redshift, and we'll cover that as well. Then we'll wrap up with the Q&A. So just starting with the Redshift development and history, it really kind of starts with Postgres, which is, if you connect to Redshift, you'll see a connection string come back, and it'll actually say that it's Postgres 8.0. And so, that's kind of the bit of the foundation. It looks and feels a lot like Postgres. The SQL is Postgres-like SQL. It's very similar to Postgres SQL. It is ANSI compatible, so it's all the SQL you love and have probably used in the past if you've used other relational databases. Obviously, Redshift is a lot more than just Postgres. We've wrapped it all up in AWS. We've added a ton of features to it. These are like analytics features. We've made it MPP. We have also, made it columnar storage. So that's really the biggest changes is, the columnar storage. And you kind of wrap all this together, and that's really what gives you Amazon Redshift. Since we released Redshift, which was actually on Valentine's Day in February 2013, just a little over 4 years ago, we've done 100 patches now, or more than. These aren't just like little bug fixes and things like that. We actually release new features every 2 weeks to Redshift. And we're going to cover some of the recently released features at the end of this webinar, and I'll kind of go through what we've recently released, but there's just, we're constantly innovating and adding more to Redshift. And these are, we roll the patches out. You don't have to do any maintenance yourself. It's all taken care of by the Redshift team. So really over the last, 4 years, Redshift has just simply gotten bigger and better. So we'll jump into the cluster architecture. This is kind of just like high level here to give you guys, some context of how it works if you've never used Redshift before. So Redshift is split into kind of two parts. There's the part that you interact with mainly, which is the leader node. That's the bit that looks and feels like Postgres. That's what you connect to with, your JDBC or ODBC drivers. You can technically connect with any Postgres compatible drivers. Such as libpq, or if you want to use pSQL, if you're used to that, all those drivers connect to the leader node. Behind the leader node is where all the data sits in other nodes that we call compute nodes, and we store the data down in these nodes. And when you issue a query, all of these nodes are the ones that actually do all of the work and send up kind of the results to the leader node. The important concept here is that Redshift is a share nothing MPP architecture. And what that means is all of these compute nodes work together all at the same time, all in parallel. And it's really about the parallelism that's really important. So if there's one takeaway from this, it's kind of understand that this is an MPP parallel architecture. Jumping into kind of the components and what makes up these, what makes up kind of the bits of these compute and leader nodes is, as I kind of mentioned, on the leader node, we have like the parser. That's where the queries are parsed. That's where we rewrite, and the planner and the optimizer and all that good stuff sits. We also have all the Postgres catalog tables. So if you're used to, the PG tables and the Postgres catalog, those actually also sit on the leader node as well. Then down on the compute nodes, as I mentioned, this is where all the data sits. In this webinar, we're going to focus quite a bit on this section, which is kind of the storage subsystem, and we're going to go through this more in depth. So just to kind of fill in the concepts of, columnar architecture, if that's not something you're familiar with, we're just going to kind of step through kind of how, what makes Redshift unique as far compared to, say, like a traditional database. That would be, a SQL database and maybe like Postgres or Oracle or something like that. So the big thing is that it's a columnar architecture. What that means is that we actually store the data on disk column by column rather than row by row. This has an advantage in that if, say, you only wanted to read a single column off disk, maybe you just want, in this particular case, only to read just the date time, for example, off of disk, what would end up happening is we only have to read just that data. And this basically results in a massive reduction in I/O. I mean, in this case, you're only going to end up having to read 1/3 of the data in this particular example. And that's one of the hugest benefits to Redshift for the types of queries that you run on a data warehouse. The next is data compression. Because we store the data column by column, it makes it really easy to compress it effectively. We can apply different compression settings to the different data types for each column independently, and they can be compressed as effectively as they can be. So if you kind of look in the top right corner there where we have the DDL for the create table, you'll notice there's the encode statements there, say encode LZO, encode byte dict, encode run length. Those are encoding types that state the compression. So that's how you put that into your compression there. The next is that we have what are called zone maps, and I'm going to cover this a little bit more in depth because it's a very important concept, but just high level, what it is we store the min and the max values for what we call blocks, and we're going to get all into blocks and all that stuff later. But what a block is if you look at those orange and white kind of squares there that are underneath each of the columns, each one of those is meant to represent a block, which is 1 meg chunks of data for each column. And then what we do is in memory we store min and max values for each of them. When a query comes in, let's say a predicate, like we're going to filter some data, we can check those min and max values in memory before we ever hit disk, and that allows us to eliminate data, or reduce I/O, I should say. And just to kind of give a bit of a better example, or to illustrate this, imagine we have some table that has these 4 blocks in this particular case with some data that's just written arbitrarily, whatever order. What would happen is if we came along with some SQL query that looks something like this, and we just want to do a count where this date equals June 2013, we can check this in-memory data structure, and we can immediately prune out a large part of the data, or well, a little bit in this case. This leads to sorting, which is a different construct in Redshift that we'll touch on a little bit. But what it does is, if you imagine you sorted your data by this timestamp, you might end up with some data that looks something like this. Now, running that same query against this sorted data, these zone maps become more effective, and we can basically eliminate all but 1 block. So that's one of the ways that Redshift can get really good performance. Picking a sort key is really kind of based a bit around your business requirements, your query patterns, that sort of thing. In a lot of cases, if you have time series data, you're typically filtering between two different timestamps. You'll usually have some sort of, maybe it's a clickstream data or something like that, or maybe some other time series data, maybe sales data that's based on time. And a lot of times you're going to end up filtering it off of a timestamp. So in a lot of cases, that first column, which is your timestamp, will end up being your sort key. And the goal here really is to make the zone maps more effective and to reduce I/O. That's kind of the big thing about what sorting does for you and how it kind of relates to the zone maps. Next that we're going to talk about is a concept that we have called slices. You can think of a slice as a virtual compute node in Redshift. You know how I kind of mentioned, we have the leader node, we have the compute node. We split those compute nodes up into what we call slices, which are kind of virtual compute nodes, and that's how we get the parallelism within each compute node. They're basically a collection of their own software processes. We store data by slice, so the data is written slice by slice. So one slice doesn't access another slice's data; it just gets its own. The next is depending on the size of the compute node, the compute nodes either come in 2, 16, or 32 slices. It's not configurable. It's kind of hard-coded for the type of compute node that you pick. This kind of leads to data distribution. How do you distribute data across all these slices in the cluster? There's 3 different ways that we have to do this in Redshift. The first is to distribute by key. What this essentially does is you pick a column in your table, hopefully a high cardinality column, and we basically hash that value and obviously send it down to do like a modulo kind of operator on it and send it down to a particular slice in the cluster. So for example, like we're going to go through kind of an example of how that works in a couple slides, so I won't go much further than that. The next is even. Even is a distribution style that really just round robins the data across the cluster, across all the slices in the cluster. So if you, for example, were like, I don't have a very good key to distribute on, I don't have something that's high cardinality, I don't have a unique key, you can just pick distribution style even and we'll take care of it for you. If, for example, in the next case, we also have what's called distribution style all, which makes a full copy of the table on each node in the cluster. It's typically used for dimension tables and stuff. So just to kind of illustrate these 3 different keys, we're going to kind of jump into some examples. The first example that we're going to end up doing here is going to be distribution style even. So if you look on the top right-hand side up there, you're going to see a bunch of insert statements there, and that's kind of the fake fictitious data we're going to use. And then we have the create table statement. You can see on the left there we have what's called dist style even there. That's how you can put that distribution style into the DDL that you normally would with your create table statement. So just moving through this example, with distribution style even, what's going to end up happening is, as I mentioned, we're just going to round robin the data through the cluster, and it's just going to move through in a very nice even fashion. If we pick distribution style key, for example, you can kind of see in the red there that's highlighted, or to highlight, I've picked distribution key location. So what that is if you look over in the data that we're inserting, we have SFO, JFK, SFO, JFK, some airport codes it looks like. If we distribute it on this, what's going to happen is we're going to get something that looks a bit like this. This is an example of picking a bad distribution key. What's ended up happening here is because there's only 2 unique values in that incoming data, we can only distribute to 2 of the 4 slices in this cluster. What that means is if, say, you were to run a query against this, this cluster, you'd end up only using one of your 2 nodes. So it's kind of distribution keys are the one thing that you want to make sure you get right over anything else. or you want to make sure you don't get them wrong, I should say. If you're in doubt, just pick distribution style even. Moving on, I'm going to try, what if we picked the primary key here, this AID, which is, unique values. Assuming the hashing worked out well, we're going to get something like this. The data is going to be evenly distributed across the cluster. Now, distribution style all, on the other hand, how it works is we're going to actually load the data all up, kind of something like this. So basically, there's a complete copy of it on each node in the cluster. So just kind of a recap and explain where you use each of these different distribution styles. You use distribution style key. If you want, it has to meet the criteria that it results in an even distribution. This is a high cardinality value, something that's not got like a kind of hot spots in it. If that criteria is met, then you can kind of continue down looking for data, what kind of distribution style you want to look at. Or you can look at further down key. So then at that point you would decide, would you, for example, are you joining this table with another large table? If that's the case and that particular key that you're joining on happens to give this nice even distribution, then that's a really good key to key off of. The next is if you're also doing, say, like group bys on that key, that can also help with performance. Or if you're optimizing for a merge join, which is kind of a special case, which I'm not going to get into in this, but it's basically if you have two large fact tables that you were, say, joining together, and this would be like, maybe hundreds of billions of rows joined with another table with hundreds of billions of rows. So kind of a special case. Our guidance for distribution style all is if the table has less than 2 or 3 million rows, you can go ahead and use distribution style all. If none of the above apply, then go with distribution style even, as I mentioned before. So we're going to get into the storage system in Redshift. One thing that I don't think we really advertise this in any way, mainly because we try and keep Redshift really simple, to use. But if you're, say, migrating from maybe some on-prem data warehouse or something like that, it kind of, just to kind of think of it like this, we actually have 2.5 to 3 times more storage on the nodes than we advertise. One of the reasons why we do that is that we mirror the data in Redshift. So we always keep 2 copies of your data. So when you write, say you do like an insert into Redshift, just you insert some data. When that commit happens, your data is safely on 2 different nodes in the cluster. So that's why we allocate that extra space. Then we also have all the space allocated for the operating system and temp scratch space and things like that. So that's why we have the 2.5 to 3 times more storage than we advertise. The space that we advertise for Redshift, like say for example like our smallest node type, which is DC1 large, which is 160 gigs, that's the usable space that you get. The next bit that we're going to talk about is what are called blocks, and I've already kind of mentioned them a couple times because it's actually hard to have the conversation about Redshift and storage and how data is stored without talking about blocks. The blocks in Redshift they're basically 1 meg immutable chunks of data that are stored column by column. And as I already mentioned, we store the in-memory bits about them, metadata essentially, which is the min and the max value and stuff like that. These blocks can be compressed. We have this one of, it's actually 11 encodings now, which we'll get to in the recently released. We just released a new encoding type. So you can set the encoding type for each column. So all of the blocks for that particular column will be encoded with that type. And then, then you can store up to, we can store up to 8.4 million values into a single block. I think that's if you were storing Booleans, for example. Then that kind of leads to, well, you have these blocks. Well, what about if you have a whole bunch of them? What we do is we call that the blockchain. So there's basically a blockchain for each column on each slice. There's technically two blockchains if you have a sort key on the table, one for the sorted region, one for the unsorted region. And then these columns can all grow independently, one block at a time, from other columns, depending on the types of compression that you have set. It's also important to note that Redshift is ACID compliant and all those sorts of things. So everything is we use MVCC in Redshift, and so there's 3 other columns to help with that you actually don't see, although you can see that they exist, but they're not queryable. And those are the row ID, the deleted ID, and the transaction ID. So we keep track of that as well. So it's kind of important to know that there are 3 extra columns in Redshift that when you create a table. So because Redshift is a data warehouse, it is optimized for batch processing. You can load massive amounts of data. A small write in Redshift costs somewhat similar to a large write. Most people will usually be loading on the order of millions of records per copy when copying data in. And that's just the way it's designed. It's designed for really big data. You can scale Redshift all the way up to storing 2 petabytes of compressed data. So typically with our compression ratio that we get, that's about 6 petabytes of data in a single Redshift cluster. Now, just kind of to note a little bit about updates and deletes, and because of the fact that it is MVCC, is that an update essentially is a delete and then an insert at the end of the table. So that means that deleted records do need to be cleaned up, and there's a process for that called vacuum. So just a little bit kind of into the design considerations here. The column properties, the bits that really influence performance are, the first thing is disk keys. They have the largest, or can have the largest, impact on performance. The next are sort keys. They would be the next, and then compression after that. So if, for example, you're tuning Redshift, maybe you're running a POC, some sort of bake-off, and it's just not performing anything like what you're expecting, definitely take a look at the distribution keys, and because that would be likely the case that would be wrong, or can be. And then the next would be sort keys. But those are the 2 that have orders of magnitude difference in performance. So we're going to jump into kind of the parallelism side of Redshift. Now we've kind of built up this foundation of how storage works and all of that sort of stuff. I kind of mentioned this, we kind of saw this slide earlier before, but I didn't really go too much into it. And what we're going to do is in the next little bit, we're going to talk about the query lifecycle, how queries move through Redshift, how data kind of comes from the compute nodes and back up. So this kind of bit here is what we're going to be talking about. What happens in Redshift is when you throw a query at Redshift, the parser obviously takes the query, parses the query. We actually rewrite the query once. This is kind of to rip out things like SQL syntactic sugar and things like that. We then feed this rewritten query to our planner, which the planner basically gets a whole bunch of plans. The optimizer, using statistics that are in the database, as long as you're keeping statistics up to date in the database, there's a command for that called analyze statistics, or just analyze, but you want to analyze statistics. What that does is it gets things like the cardinality, of the column, it kind of samples a bit of data about it, and that allows the optimizer to pick the correct, or hopefully the correct plan that is going to fulfill the query, get the results as fast as possible. We then pass that through to a code generator, which generates a bunch of C++ code, and then we'll send that down to the compute nodes, and every compute node will then execute that C++ code and send up the results. So just to kind of go through how this kind of works a little bit deeper, I'm going to start talking at the bottom there of this slide, which is a stream. A stream is basically a set of these C++ programs that I talked about, these C++ binaries. So there could be multiples of them in a single stream. Each of these streams is basically built up of segments. Actually, those are the C++ bits of code. And then obviously each of them is built up of a bunch of steps. So just to kind of visualize this, imagine you had some query. Maybe this query has a couple subqueries and a join and things like that. And to fulfill this query, we're going to end up needing to generate a handful of streams. What's going to end up happening is kind of take a look at the top one. You have stream 0. The Redshift would have, in this case, generated 4 segments, which are basically individual kind of C++ programs. These can run independently all at the same time, which is really awesome because you can get more parallelism. And then each of them is built up of a bunch of steps. Then what's going to happen is obviously you can't move from one stream into the next stream until you have the previous stream is complete. So kind of to illustrate all of this, imagine you come along with some client and you want to, you issue some query with your favorite driver or whatever you're connected with, JDBC, ODBC, and you connect to the leader node. The leader node is obviously going to parse that query. You're going to get some query plans, get the explain plans. We're going to figure out the best one to have. You're going to hit the code generator. The code generator is going to basically generate some code and send it all down to the compute nodes. The compute nodes are then going to execute this query, and they're going to go through all of the segments and all the steps in the segment. And then they're going to send up the results once this stream is complete. Then what's going to end up happening is in this example, we're going to end up generating a second stream using those results. Once that happens, we're going to get the results sent back down, and this is the second stream executing here, and then we're going to send that back up again. And there's no more streams at this point, so then we're just going to send back the actual final results. Now there's an important thing here that kind of happens. Say imagine you were doing maybe some summation of data. You were doing some sort of sum, some order buys, and there's maybe a limit at the end of this and all that kind of stuff. The leader node actually does the last bits of this, right? Because both of the compute nodes, they might have summed up all their data, and then you send it to the leader node, and then it kind of has to do that kind of final summation, and then maybe you have an order buy in there, and then the leader node ends up doing the order buy and applying the limit and that sort of stuff. Once the leader node has done these things, it then sends the final results back up to the client. There's also one extra bit that I didn't really bring up earlier in this, and that's that if any of you have used Redshift before, you'll kind of come along and you'll type out some query, maybe say select count from some table, and you notice that the first time you run it, it takes like an extra couple seconds. What that is that's the compilation step that you're waiting for, and that's what we end up doing is we cache those compiled plans. So that's why the second time you run it, it's really fast. Even if you, say for example, you came along and you wrote a query and you had a filter of some sort of predicate and you were like where something equals something, and the first time it has that compilation delay. After that, what's going to end up happening is even if you change the parameters in the query in your where clause, it'll still use the same compiled query. So that's one thing to be aware of is that we do cache these compiled binaries, and they'll even persist through cluster reboots and everything like that. The only time we really wipe them out is in the maintenance cycle. So they do get wiped out, when we come along every couple weeks and go through maintenance. These next couple slides, they're basically what I just talked about, this slide and the next one. So if you want to, when this gets put up onto, if you just want to read through the slides at some point, maybe you're up on SlideShare, you can kind of read through. So I've kind of just put up all the notes to explain what's happening. And this is just kind of a repeat of what the segments and steps and sort of that sort of thing is. And the reason why is to kind of show you, obviously this is happening across all of the slices, across all of the nodes in the cluster at the same time. So continuing the theme of parallelism, if you guys are looking at maybe loading data into Redshift or trying it, obviously you guys are interested in it because you're here. If you're looking to load data into Redshift, one of the things with that kind of, you have a good foundation of slices, is the loading data. What we're going to end up having here is, this is an example with a fictitious cluster, just a single one-node cluster, which is a DS2 8XL. This particular cluster has 16 slices in it, because that's what that node type has. And what we've done here is imagine we have a CSV file that we're going to load into the cluster, just a single one. And so we go, hey Redshift, here's some CSV file sitting on S3, go load this. And so what will happen is it's one of the slices in the cluster. We'll go and download the file, and it'll pull it up and parse it and distribute it and get it written across the whole cluster. And that'll work just fine. The problem is that you're only using 1/16 of the cluster. That one slice is essentially doing pretty much all of the work. So if we took that same file, maybe just pretend it's like a 1 gig file or something, and we split it up into 16 files, maybe whatever your ETL process is to get the data on S3, before you drop the files on S3, you split it up into 16 files. Then in this case, if you go, hey Redshift, copy these 16 files in, what Redshift will do is it'll basically get every slice in the cluster to load a file. So the guidance around here kind of is that you'll want to have one file per slice, or some multiple number of files that's divisible by the number of slices you have in the cluster. So in this case, you could have 32 files. That would be totally fine. That just means each slice gets 2 files to work on. Or you keep going up, you have 64 files or whatever it happens to be, and that'll completely work well. The files ideally should be at least 1 meg in size and less than 1 gig. So between 1 meg and 1 gig after gzip compression. You definitely get a big benefit from gzipping the files. It reduces the amount of network I/O that we need to do, and so yeah, huge benefit to do that. So kind of, I think this is a bit of the fun part up here. We're going to kind of go through just some of the new stuff that we've released. The first one is that this is last October timeframe, we released what we call node failure tolerance. So this is like when node fails, and we'll hold all the connections and everything now, so that while the cluster's being fixed up, it takes on the order of minutes to replace a down node. The connections will all be held and everything like that. The next is that we then released a new data type, timestamp with time zone. So that was kind of a big ask. A lot of people want, it was something that was in Postgres that we didn't have. The next feature that we also released recently was automatic compression with create table as syntax. So if you've ever used, the create table as and some select statement, what would happen in Redshift previously is that you didn't get any compression settings applied. Now we figure that out and we'll apply compression for you. Another one that was kind of a big ask was limiting users' connections. You kind of got like, some user, some analyst or someone that would connect to Redshift with 50 connections or 100 connections and kind of, start saturating up we have a 500 connection limit in Redshift, so they'd start taking up, a ton of the connections. So you can apply now connection limits per user. The next is a kind of a special feature in a way. It's actually a feature where if you have a single sort key and you're adding data in sorted order, Redshift will just figure out that the data is sorted and you won't need to vacuum your tables in any way. The next is a security feature called enhanced VPC routing. What this does is it forces Redshift to route data through your VPC when connecting to S3, and this allows you to place VPC endpoints, policies onto the connection so you can restrict which buckets and stuff that Redshift can access. 2016 was a huge year for performance for Redshift. The team focused just massively on performance. Vacuum saw a 10x performance increase. In some cases, it was more than 100x in certain scenarios. Snapshot restore is twice as fast as it used to be. And queries, we saw several times performance improvement, 3-4x performance improvement pretty much across the board. The next, this is a brand new feature. I was actually, when I was going through these slides and putting them together, I just wanted to grab the latest features for you guys. And this one was, I didn't even know that this one had come out until I was going through these slides. And this was the Z standard, which is a new compression type that we've added to Redshift. And what that is it's a new compression type. It was, I guess, built by Facebook, and it gets quite a bit better compression ratio than LZO. So yeah, new compression type that's been added. The next is to make migrations easier. SCT stands for Schema Conversion Tool. What we've done is Oracle and Teradata, it can do a one-time push or pull of data out of those two platforms and into Redshift. So Schema Conversion Tool, it's a kind of a standalone product. It's free. You can download it from the AWS site, and you can connect it to a handful of different databases and data warehouses. And what it'll do is it'll go through your schema, and it'll convert it as much close as it can to Redshift schema. So you're totally useful, or really useful application to make migrations a lot easier. It'll get you probably 80% of the way there, and then you can kind of tweak the last bits yourself. The next is upcoming features. So these are a handful of features that are kind of exciting. The first one, I noticed in the last slide, I kind of was talking about node failure tolerance, and I was like, okay, connections are parked. So what we're going to end up doing going forward is we're going to end up resubmitting queries and such for you. So this will kind of make node failure tolerance kind of really fully featured in that you had an in-flight query, well, a node went down that just happened to be timed that way. We'll figure that out and resubmit it so you don't even notice that a node went down. The next is we're going to add what are called query monitoring rules. These are rules that can be set up to basically, if say you have an analyst or someone that's maybe writing bad queries, they come along and they do some Cartesian product or something crazy, something that's going to return billions of rows. This allows you to set up rules that detect those bad queries and kill the query. And basically to save the cluster resources for other, more meaningful queries. The next is a feature that we're calling short query bias. And what that does is that, imagine you have like a whole bunch of queries that are hitting the system. Obviously queries queue up at a certain point. They wait for the queries before them to finish because it makes more sense to do that. What we'll do is we'll detect that a query, while it's coming in, we can kind of roughly tell how many rows and how much data it's going to scan. We're going to analyze that and figure it out, and we're going to push it to the front of the queue if it's a short query. The next is power start. What that is that kind of ties in with short query bias, and power start basically is a query, when it begins executing, will basically be given a whole bunch of resources in the system to get done and out of the way. Now, the whole idea around these two features is basically to let you want to have the short interactive queries finish quickly. And so, a query that takes, 2-3 seconds, you want it to kind of be done in 2 or 3 seconds. A query that takes, 15 minutes, if we kind of slow them up to make sure that those short interactive queries get done, and instead of a long-running query taking 15 minutes, it takes 18 minutes, that's probably fine. And most people aren't going to complain about that. So that's kind of where we're going with that. Try and figure that out for you. The next is vacuum. So we're going to be coming out with automatic vacuum. That's one of the next upcoming features that we're also working on. For now, we have a really good utility that we've released onto GitHub. It's on the Redshift utils, and that's, it's on we've released a whole bunch of utilities and useful queries and all that kind of stuff onto GitHub. And there's one on there for vacuum and analyze, and you can schedule that utility with cron, with whatever makes sense, for your, depending on your query patterns and such. And yeah, so you can use that for now, but in the future, we will want to take care of that for you as well, because we want to, make Redshift as easy to use as possible. The next is IAM authentication. Right now, all of the authentication stuff in Redshift is covered, it's all managed in Redshift, all the usernames, all the passwords, all that kind of stuff is in there. We want to, we're going to link that in with IAM, so you can authenticate using IAM as well. The next is, I'll just mention the last one at the bottom there, and then I'll jump up. So approximate percentile functions, we're going to be releasing some new approximate functions in the near future. And then the next is back to the schema conversion tool, we're going to be adding support for both Vertica and SQL Server so that you can convert schemas from both of those systems. Those GitHub utilities that I mentioned, these are some of the links that will kind of get you there. And the vacuum one actually isn't called out on this slide here, but it is up on the site there. The couple others that are worth calling out, the admin scripts, what those are is they're a handful of scripts that our database engineering team, the solution architects like myself, have kind of found useful, and we've basically added those up there. They're actually scripts that we run on a very regular basis when we're working with Redshift, and so that's why we've added them up there. The same thing with the admin views. A couple in there that are worth calling out is the ones that generate schema for DDL. Definitely, if you're wanting to, you're a DBA type person, you'll probably want to end up going through the admin views and creating a handful of those as well. The last one there is a column encoding utility, which can be used just to encode data and such. So that concludes this portion of the webinar. We're going to jump into the Q&A at this point here. Thank you.
And thank you, Tony. Thanks for the great presentation. I'd also like to thank Ho Hong and Peter Dalton for engaging the audience throughout the presentation with our Q&A answers. On your screen, you'll see 3 polls at the bottom of the screen and 1 at the top. We do value your feedback, so please take time to complete that. We also have your Q&A pod in the upper left where you can continue putting your questions in for our session. We're going to start our Q&A session.
The first question here that's kind of rolled in is, when will you allow copying data from a table in one database to a table into another database without having to use unload and copy? That has actually been a commonly asked question lately. I don't have any kind of feedback on that or when we're going to be adding support for that or anything like that, but definitely pass that along to our product management team. Thank you very much for that. The next question is does Redshift have any tools, processes which look at each query being executed and suggest better compression or move data between nodes for better execution time? The first bit is we do have a tool for better compression. There's one built in a Redshift called Analyze Compression, but really all that one does is it just it basically just gives us suggestions. If you want to actually have it apply the compression and recopy the data and move it all, that there is a utility on GitHub for that that is very commonly used, and it uses a combination of Analyze Compression and fully copies the tables and such for you. The next question is around partitioning. Why doesn't Redshift have a concept of partitioning? Right now it is true that we don't have partitioning in Redshift. Most customers, what they'll do, there's 2 kind of reasons for it. The first is in many, or if not most cases, most customers don't need it. That's not to say that there aren't cases where it is needed. So when customers do need it, the workaround really is to kind of create multiple tables and layer over top of a union all view. We've been improving the union all views significantly over the last year so the query there is performant, hopefully as running it against a single table. There is obviously a little bit of maintenance in that you have to recreate the view when you add tables, and essentially which you're using as partitions under the hood. The next question is backups. How are they done, and is there a cost? Yeah, Redshift backs up basically continuously, asynchronously in the background. What it does is every 5 gigs of change data in the Redshift cluster, the backup process will kick off and it'll synchronize the data. If 5 gigs of data haven't changed for a period of time, it's 8 hours. So the most you'll usually be lagging behind is 8 hours in your automated backups, and they are free. It's fully included in the cost of Redshift. So your Redshift's all-inclusive pricing, so backups are totally free, or well, included, I should say. I think that's about it for questions. I'll wait another 15 seconds if there's any other questions, but I think that's about it. Thank you, guys.
Well, I'd like to spend a special thank you here to our presenter today, Tony, for the great time and the presentation that you were presenting with us today, and of course our moderators today, Ho Hong and Peter Dalton, for answering the audience's questions today. If you have any comments on the previous or upcoming webinars or suggestions on the topics you wish AWS to cover in future webinars, please feel free to email us at aws-webcasts@amazon.com. Your feedback will help us improve our webinar programming. Thanks to everybody for joining today. At this time, you can disconnect.